In this video we're going to look at how repeating a measurement can provide useful information about a sample through XPS. The data set in question is an exaggerated form of such a measurement, but nevertheless it's an important insight into this particular sample. And the sample is a molybdenum 6+ oxide, and it's been measured 24 times. And the data set is such that when we overlay spectra from this molybdenum 3D doublet, where instead of seeing a well-formed doublet peak, we see a series of peaks that evolve in binding energy from a lower binding energy state up to a higher binding energy state. And this in itself is giving us some information about this sample and how it's reacting to measurement by XPS. The reason peaks move in binding energy is related to the charge compensation. And there are several scenarios that can be used for charge compensation, and it depends on the sample itself. So if you have an insulating material and you do not connect it to ground and there is no charge compensation, you will end up with a positive charge building up on the surface, and the result of a positive charge is that photo-emission electrons that are negative are attracted back to the surface, so we tend to see peaks shift to lower kinetic energy as a consequence of a build-up of charge on the surface that is positive. Another scenario is that charge compensation is performed, we have no ground connection, and so a charge can build up on the surface which might be negative. In this case the peaks shift to a lower binding energy, a higher kinetic energy, and this is because a negative charge will repel electrons that are emitted as part of photoionization. And then another scenario is that we connect the stage to ground and the sample to ground, and if this is a metallic material, then the result is that electrons leaving the surface are compensated for by electrons moving through ground, through the sample holder and into the sample. So we end up with photo-emission peaks that appear, provided the instrument is calibrated in terms of work function, at the binding energy or kinetic energy that we expect for a given photo-emission process. However, there is another scenario, and this is the scenario that relates to the data we're going to look at, is that the sample is grounded. So electrons can move to the sample from ground, and charge compensation is also active, and so a cloud of low energy electrons are being returned to the sample. So we have the situation where for an insulating material we could potentially have a negative charge build-up on the surface, and for a conducting sample excess electrons would move to ground or be replenished by electrons from ground if there is a deficiency. And so we ought to be able to measure a metallic sample and potentially an insulating sample with similar ease. But if we have a material that for some reason changes during the course of a measurement, then this relationship may cause problems. In what follows, I'm going to work through this VAMAS file and organize the data in such a way that I can understand and give an explanation of what I think is happening to cause the movement of these peaks in binding energy. This is a VAMAS file that contains spectra from 3 different samples, and each sample has been measured multiple times. When the VAMAS file is displayed in CasaXPS, the logical structure of the file is organized according to the element transition fields and the experimental variable. The experimental variable organizes the rows and the columns by the element transition fields. So we have all carbon in one column and all oxygen in another column. In this case, the organization of the file is not well represented by the experimental variable that is assigned the etch time. The etch time is identical for all measurements. So we need to choose a different experimental variable that will allow the true organization of this data file to be displayed within CasaXPS. Not all VAMAS files will necessarily have experimental variables that will allow a differentiation between the different samples within this file. As an alternative to using the experimental variable, there is a string associated with each spectrum, which is the sample identifier. And if this has been assigned, then using the edit mode button on the toolbar will then redisplay the data, showing the relationship of the spectra with respect to the sample identifier. So here we can see that the first experiment is based on molybdenum 4+. The second one is, as we can see here, based on molybdenum 6+, and the third is described as molybdenum oxide. Since this file does contain experimental variables, that's to say more than one experimental variable has been assigned to each VAMAS block, what I'll do now is I'll cycle through the experimental variables and illustrate the different experimental variables and how these data are then redisplayed based on a selection that I'll make using the select menu and say next experimental variable. So we have a position index now, and we can see from the position index based on the sample position, that is to say an index each time the stage has moved is recorded and appears in the VAMAS file. So the first experiment has a position index of 1, the second 2, and the third is 3. Other experimental variables that may not make sense for a given measurement that were assigned, for example angle, so this may be a tilt, this is all the same, it's all 0, so that doesn't help much. There's another one that is sputter time, well that is related to the etch time and there's no etch time, so that doesn't help. And then the next one in this file is the date stamp index, and what this experimental variable is indicating is that each spectrum that you see in a row has all been assigned the same date stamp when the acquisition commenced, and the index is incremented each time the time at which a measurement is performed is incremented. So we can see here a sequence of different acquisitions that were performed with different date stamps, and in looking at the data in this way we can see that the data appear now in blocks corresponding to the different samples, and we can see which sample is which by looking at the data using an option that says use ID title, and this then adds to the title this sample identifier. So when I display this oxygen 1s, we can see this is the molybdenum 4+ oxygen 1s that was the second sequence of this first set of narrow scan spectra. If I look at the oxygen 1s from the second group, we can see this is a 6+, and from the third group you can now see this is the sample identifier molybdenum oxide. So we're able to see now, using the experimental variable and the sample identifier, the relationship between spectra within the VAMAS file. Analysis of a data file is enhanced if we understand how data are organized. It's also important in terms of quantification. If you want to compare intensities from different elements from the same sample measured at the same time, it's important that these are all collected together in such a way that we can easily identify spectra that belong to the same measurement. So this is an important part of analyzing data, is to maintain an integrity of the data that are collected at the same time. Now we might want to examine, for example, the molybdenum 3D from the molybdenum 4+, and because of the arrangement we see here, I can do this by making a selection of the molybdenum 3D VAMAS block that corresponds to the first one in terms of the date stamp, and then go to the last in the column holding the shift key down before left clicking the mouse, and then I make a selection of all of these molybdenum 3D spectra in the right hand side. Then I can overlay these using the overlay F2 button on the toolbar. So now we see all of the spectra, they have a very similar look to them. These quite reasonably would be assumed to be molybdenum 4+. We can similarly use the same mechanism to have a look at the oxide. So click and then shift click to make a selection, and we'll overlay again. And again, spectra, very similar spectra. It's not unreasonable to assume that these were all measured from the same sample. And the reason this is important is that we might want to do some type of comparison between different experiments that are from related samples. And in this case, there is evidence that suggests that what happened to the molybdenum in the 6+ state is not the same as I've just shown you for the 4+ and the molybdenum oxide. That the spectra that correspond to the 6+, when I overlay these, instead of looking well behaved as the other two data sets did, these do not. So what I'd like to do is try to understand what has happened in the case of the measurement of the molybdenum 6+ and why it differs from the case of the 4+ and the molybdenum oxide. To understand the evolution in these data, it's probably better to use a different palette of colours to display the data. The colours we see right now displayed here in the right hand side correspond to the spectra we see in the left hand side, and they are from a palette of 16 colours that you can select at will. However, there is an option that allows us on the colours property page of the tile display parameters dialog window to use a scale of colours rather than a palette of colours. So the idea is there's an evolution in the colour scale, and that will reflect an evolution in the data. If I tick the box display spectrum using scale and then apply, we end up with a colour scale that gives us a better idea of how this evolution occurred. The colours are marking this selection in the right hand side, so you can see the initial position for these doublet peaks is at a lower binding energy, higher kinetic energy. So if I look here, you can see that the binding energy is about 231 eV. And then as the evolution occurs, the last spectra that were acquired, it's more like 232.3. So an evolution is occurring, and one explanation for such an evolution is that the sample is charging positively with time. If it charges positively with time, that means that electrons are retarded as they leave the surface and they lose energy. So that would be the basic explanation. However, there is another explanation that is related to how these data were acquired. All three data sets from three different samples were acquired using charge neutralization and also connected to ground. That is to say, the sample is connected to ground, so electrons can move through the ground to the sample holder and onto the sample. Now in the case of the first two measurements, both have metallic character with a small amount of oxide. So the overall influence on the sample is that of a metallic type material. So even though electrons were being returned to the sample by the charge compensation, they were easily distributed and moved to ground if necessary to keep steady potential on the surface. In the case of the molybdenum trioxide, we have a material that has a significant band gap. It's about 3 eV initially. However, over time and with each measurement, something has changed in the sample, which means that molybdenum trioxide as a semiconductor needs charge compensation, and the fact that the peak is offset towards the lower binding energy side tells us that electrons were accumulating on the surface and a steady state to some extent was achieved, and therefore you end up with a peak for the 5/2 component that is somewhere at an energy that is too low in binding energy for what we would expect for molybdenum trioxide. However, with time, the peak moves and ends up at an energy which is in fact more consistent with what we would expect for molybdenum trioxide, that we're looking at a binding energy for the 5/2 peak after the sequence of measurements that is closer to what you would expect for a conducting form of molybdenum or a neutral form of molybdenum trioxide. So to summarize, the fact that these data were measured with dual charge compensation available, that is to say charge compensation through electrons of low energy returning to the sample and also connected to ground, meant that with time and an evolution in the material as a consequence of the measurement, the roles played by these two mechanisms has interfered with a stable peak position, and we've gone from a position that would be compatible with charge compensation through low energy electrons initially to a position that would be compatible with electrons returning to the sample through the ground, which is similar to what you'd see in the other two samples. So the importance of isolating a sample from ground when using charge neutralization can be illustrated through this observation.